This video is the second of two videos to talk about analytic functions of complex variables and mappings. In the first video, we talked about functions of complex variables, and we started by saying complex variables are represented by two numbers, an x-coordinate and then a y-coordinate, representing the real portion of the complex number and y representing the imaginary portion of the complex number. So when we have a function, we can't just graph in two dimensions where our x-coordinate is our input and our y-axis is our output. In fact, our input is a two-dimensional object and our output is a two-dimensional object. So we have this kind of function, sort of a mapping kind of way of representing our functions, where we say here is our input and we have a complex number z, which then gets mapped to our output, which we call the UV plane, which gives us a complex number w. So f of z gives us w. So it's a mapping from the xy plane to the UV plane. The next thing we talked about is mappings boil down to translations, rotations, and reflections. And in fact, reflections are just a special case of rotation. So translations we saw corresponded to addition of a complex number. So when you add a complex number to another, you translate your original complex number. So for example, if z is a complex number and we add 1, which is equal to 1 plus I times 0, when we add that, then 1 gets added to the real portion, nothing gets added to the y. So this corresponds to translating each point 1 unit to the right. Similarly, we can make an argument if we added some component I. That would translate your vector 1 unit up along the y-axis. We saw that rotation corresponds to multiplication by a complex number. So if we have a complex number z and we multiply by e to the I theta prime, then what we get is r e to the I theta plus theta prime, and you can see the derivation. So that means this multiplication by e to the I theta prime rotates the vector, your original vector z, counterclockwise by theta prime. And then we also said reflection, the complex conjugate corresponds to complex conjugates. What we are going to do in this video is we're going to analyze different mappings. We're going to do examples. We'll look at this by example. But the three common ways of analyzing a mapping is, one is to convert to polar coordinates and analyze translations, rotations, and reflections over here. The second way is to look at our z equals uxy plus ixv, to look at this and to hold uxy constant and then see what these constants translates to or transforms to, and then similarly going and holding v of xy constant. We'll do an example of that. And then last is sometimes we take entire regions, not just constant lines, but we'll take an entire region, often a rectangular region, to see how that gets mapped. We're going to go straight into this example considering f of z equals z squared, and we're going to analyze this by holding u of xy constant and then v of xy constant. And I will also mention that we did analyze this in the previous video by converting to polar coordinates and analyzing in terms of translation and rotations. We will start again at f of z equals z squared. And I have my expansion of f of z equals z squared, which is x plus iy squared, which is x squared minus y squared plus I 2xy. And I have my u function here and my v function here. So first we'll look at if we hold u of xy constant, let's say it's equal to c1. In our graph, we're looking at something like this in the uv plane. We're looking at holding u equal to c1, greater than 0. Then what we see is then our u of xy, which is equal to x squared minus y squared equals c1, is a hyperbola with vertices at plus or minus square root of c1, 0. And for your reference, I have the equations for hyperbolas here. Notice since the x squared and y squared terms is equal to 1, for our equation for u is equal to c1, to see the hyperbola, we have to divide both sides of the equation by c1, and then also our h and our k terms are 0 here. So that means our vertices are h, which is 0, plus or minus a, which is going to be our square root of c1, and then k is also 0. So this is where we get the vertices, square root of c1 and 0. And then here is where I have the drawings. So we have this hyperbola with vertices at square root of negative c1 and square root of c1 that gets mapped to the straight line. We know u1 is fixed. If we want to see how v gets traced out along this hyperbola, what we can do is look at our equation for v, which is equal to 2xy, which is equal to 2yx, and then I can solve for x using my equation of u of xy, solve for x in terms of y and c1. So that's what this is. This is x in terms of y and c1. So this is my equation for v, and y goes between negative infinity and infinity. So as y here increases, you can see that my v is also going to increase. And I'm going to indicate that with an arrow. So as y increases, I'm going to say v increases. And this is what we have here for this right-hand branch. The left-hand branch of this hyperbola, that's where u is equal to c1, and we take the other branch of v, so v is equal to 2xy, and remember that's 2y times x, but remember x now, because there's a square root, there's the positive, which I already used for the right hand, and the negative square root, which gives us this left-hand branch here, as y goes from negative infinity to infinity. So you can see this increases as y decreases. So this is the arrow I have here. So we have v increasing as this value on this branch, y decreases. So that's what this arrow here is indicating. We can do a similar analysis when v is set equal to c2, when v is a constant, this blue line here. And what we see is v equals xy equals 2, xy equals c2 is also a hyperbola. These are the blue hyperbola here. And we can trace out u doing a similar thing where we substitute u is equal to x squared. And now we use this equation, 2xy equals c2, to solve for our y squared in terms of x and c2. In other words, y is equal to c2 over 2x, since we have u is equal to x squared minus, now y squared would be c2 squared over 4x squared. So again, this is an example. If we have a complex function, sometimes we want to know where the straight lines get mapped, or what things, in this case hyperbolas, get mapped to straight lines. And now we'll do more examples, just getting used to, again, the complex functions, some of these mappings, and other types of way of analyzing. This first example is to identify u of xy and v of xy if f of xy is equal to modulo z squared. First, we're going to write out modulo z, which is square root of x squared plus y squared. And now if we want to square that, that would be squared. So we get x squared plus y squared. So u of xy is x squared plus y squared. And there's no imaginary part by the time you're done with modulo. Modulo is, after all, a distance. So v of xy is equal to 0. This next example is to express in an exponential form the function f of z equals z to the 1/2. The first step is to express z in exponential form. So that's equal to r e to the I theta. Then z to the 1/2 is square root of r e to the I theta over 2. Now because in polar coordinates, our radius is always positive, and of course an in complex numbers, e to any exponent is always positive. We take only the positive square root, and we get z to the 1/2 is equal square root of r e to the I theta over 2. I'm sorry, this is not pi, this was theta over 2. The last example is to analyze w equals e to the z. And we're going to use these last two things. We're first going to consider holding different lines constant, and then last we're going to analyze a region, in particular a rectangular region. We will start by writing z as x plus iy, so we have e to the x plus iy, which is e to the x times e to the iy. And I'm going to write this as rho to emphasize this is a radius. E to the x is our radius, and e to the iy, if we were writing this in exponential form, then y is our angle. In this case, we're going to call it phi. We're going to hold x constant at c1. So what happens here? So if we have z equals c1y, so w of cy of c1 plus iy will equal to e to the c1 e to the iy. So now what we have is a circle of radius e to the c1. I can draw this here. So in the xy plane, I have values of x that's equal to c1, and that's going to get mapped to the circle of radius e raised to the c1. And one of the interesting things is, remember, this is kind of this infinitely long line mapped on a circle. So you kind of get the feeling this is going to map on the circle several times. In other words, it's going to traverse or trace out the circle several times. And in fact, the image of x equals c1 is the entire circle, and each point of the circle is the image of an infinite number of points spaced 2 pi units apart. So in other words, here we go from 0 to whatever, some number, and that'll, here, let me actually do this, and that'll traverse the circle once. Now from here, if this is our period, then our next 2 pi space will traverse the circle another time. Similarly down here, same period, same amount of space, is going to traverse the circle a third time. So in other words, each point here on the circle is the image of an infinite number of points. In this case, we've drawn maybe 3 times, like one point in here, 1 point here, and 1 point here. So spaced by 2 pi units apart. If we continue our analysis now to look at the image of a point on the horizontal line y equals c2. So now we're going to hold y equal to a constant. So z is equal to x, y is equal to c2. So w of x plus I c2 is equal to e to the x, e to the I c2. Here we are on this slide, y equals c2. Now as x increases, our radius is going to increase. But here our IC2 is going to be held constant. So our angle is held constant at theta. So an angle is constant as our radius increases. So these horizontal lines here get mapped to a ray where the angle between the real axis, the positive real axis, and the ray is equal to C2. Last, we're going to use the same problem to analyze a region, in particular a rectangular region of the xy plane, which is the easiest region to analyze in the xy plane. And actually, we'll do 2 examples, 2 regions. I've summarized our work here where we held u and then v constant. And we're going to go on and look at transformation of rectangular regions. So in particular, we're going to show that the w e to the z transformation wraps the rectangular region shown here. That is, x goes between a and b, and y goes between c and d, so we get this rectangle, onto rho being the radius between e to the a and e to the b, and phi being the angle between c and d. And this is a from over here and b from over here, values of x, and c and d being values of y. To see this, let's start with the line AD over here. So I'll highlight that in blue. So AD, what we want to show is AD then is mapped to this curve AD. And we start by looking at AD, and we see that the x value at AD is equal to a, little a, and we see y varies from c to d. And now we look at w of x plus iy, that's equal to e to the x, e to the iy. So I rewrote that here. And then in terms of my x's and y's, that means we have e to the a, e to the iy, where I goes between c and d. So in other words, our radius now is equal to e to the a, and that's what we have here. Our radius is equal to e to the a, and that our phi goes between c and d, and that's what I've drawn here. Phi goes between c and phi equals d. I didn't really say the radius here, but you'll have to know that the radius here is equal to e to the a. Similarly, we can show that the line BC over here in green is mapped to the arc B prime C prime over here in the UV plane, with rho, the radius, equal to e to the b. So we can look at BC, this line, and here we see the line BC, x is equal to b, and y varies between c and d. So again, looking at our w, x plus iy is equal to e to the x, e to the iy. Then this means this is equal to e to the b, since x is equal to b, and then e to the iy, where y varies between c and d. So here, again, we have our phi, our angle now varying between c and d, but our radius is out at EB, which is greater than EA, because here we have B greater than A. So we have this arc here, goes from phi equals C to phi equals D, and again we are at a radius EB, which is greater than EC. And another note, the map is 1-to-1 if D minus C is less than 2 pi, right? So if we don't keep having multiples of 2 pi, we're not going to keep tracing this arc over and over. So in particular, if C equals 0 and D equals pi, then when we map from 0 to pi, since our phi goes from C to D, that means we're going to go from phi equals 0 to phi equals pi. So we're going to trace out this circular ring. And again, this radius here is e to the a, and this radius here is equal to e to the b. So the ring is the interior right over here. I've moved all of this up now so we can do this last part of this problem. Show the image of the infinite strip y goes from 0 to pi is the upper half, v greater than equal to 0 of the w plane. Pictorially, what we have is this strip y from 0 to pi gets mapped to the entire upper half of the w plane, or the uv plane. So we look at w x plus iy, which we see is equal to e to the x, e to the iy. So for example, e to the x plus I pi, when y is equal to pi, gets mapped to e to the x, e to the I pi. Or when y is equal to c1, then wx plus I c1 is equal to e to the x, e to the I c1. So what we look at is, let's say for example, we're at y equals c1. So we are on this angle, c1, and as x increases, our rho increases. In other words, here, as x increases, then we're held at phi, our angle, c1, but as x increases, we kind of march out along this ray here. So with rho increasing, we get the ray phi is equal to c1. So we get this entire ray for x is equal to c1. And now, if we consider y ranging between 0 and pi, so for 0 and pi, when we have 0, we're going to get this ray. When we have pi, so pi is over here, we're going to have this ray. When, let's say, y is equal to pi over 2, so we're going to get the pi over 2 ray here. When y is equal to pi over 4, we're going to get the y equals pi over 4. And so we basically just get all of these rays until eventually we've covered the entire UV plane. So this video, which is the second of 2 videos on analytic functions and mappings, we focused on analyzing the mappings. We looked and actually in the previous video, we looked at converting to polar coordinates and then analyzing translations, rotations, and reflections that we had talked about in the first video. In this video, we looked at holding u of xy and then v of xy constant, so looking at lines and seeing how they translated over. And then later, we did a couple of examples where we analyzed regions. Often these are rectangular regions that you do because they're the easy ones in the xy plane. And that sort of summarizes what we did in this video. I'm sorry that I had to break my video into 2 parts. I guess I was really ambitious and thought I would cover all of this in one video, but it got quite long. But anyway, that's it for this video and the videos on analytic functions and mappings. Thank you for watching.